Okay, equilateral triangles. What was our formula for the area of an equilateral triangle? Okay, root 3 over 4 s squared. The root 3 over 4 is a coefficient. Do I put it inside the integral or outside, or does it matter? It really doesn't matter. I kind of like to keep them outside. Almost all of them have s squared. Well, let's find out. But the integral of 2x squared is the same thing as 2 times the integral of x squared. You can pull a coefficient in or out. You can never, ever pull a variable out. Okay, C, rectangles of height 1. What would the formula for a rectangle that has a length of s and a height of 1 be? Just s, right. So C is just the integral from negative 2 to 3 of negative x squared plus x plus 6. Well, if your rectangles, the length of your rectangle is going to be the length of this rectangle right here. Yes. Right. Okay, very good. I should have pulled down one that had rectangles. If your cross sections are rectangles, then the roof or the height of the building is going to be uniform throughout the whole thing. Yeah, so if it had a rectangle, let's say if it was rectangles of height 4, then I would just need to stick a 4 out in front of the rectangle because the area would be 4s. Okay, D. What's the formula for isosceles right triangles? 1/2 s squared. And I'm going to get even lazier right here, and you're welcome to do this on your homework. If you've identified s as being negative x squared plus x plus 6, then you are welcome to just write s squared. All right, and then what would E be in terms of s? Yeah, 1/8 pi or pi over 8, integral from negative 2 to 3, s squared dx. Okay, now, is it a problem that I've got s squared and a dx, that the s and the dx don't match? No, because s is in terms of x. All right, so in example F, the cross sections are supposed to be rectangles with a height of square root of x. And this is a little different than all the other formulas that we've talked about, but we're really working it exactly the same way. The formula for a rectangle is the length of the base times the height. Well, the length of the base of this rectangle, all these rectangles, is still going to be s that we've identified, and then the height is absolute value of x. So if we're integrating the area of the rectangle, then we will integrate the height, which is the absolute value of x, times the length of the base, which is negative x squared plus x plus 6 dx. And like all of the others, the limits of integration go from negative 2 to 3. And if you type that into your calculator, you should get 21.083. And a lot of times the height of the rectangle will just be a constant, like the height will be 4. And in that case, we can pull the 4 out in front of the integral because you can always pull a coefficient out in front of the integral. But if the height has a variable in it, you cannot pull that out in front. So you can never, ever pull a variable in or out of an integral. You can pull a coefficient that's just a number in or out, but you can never pull a variable in or out. So this is the only way to set that up. All right, for example 3, we're going to find the volume of the solid whose base is bounded by the equations y equals negative x squared plus 4 and y equals 0. So we've got this same parabola. And the line y equals 0 is along the x-axis. So here's my region. This time, however, the cross sections are taken perpendicular to the y-axis. So this time, S is the horizontal distance or the horizontal length of that rectangle. And anytime we have a rectangle that's horizontal, the length of it is the right side minus the left side. But in order to do the right side minus the left side, we're going to have to solve the equation for x. And we also know this because the thickness or the width of that rectangle is dy. So everything has to be in terms of y. So I need to solve this equation for x. So when I solve this equation for x, I get x squared equals 4 minus y, or x equals plus or minus the square root of 4 minus y. And once again, the right side of this parabola is going to be the positive square root of 4 minus y, and the left side will be the negative. So the length of this rectangle, or the length of S, is going to equal the right side minus the left side, which would be the square root of 4 minus y minus a negative square root of 4 minus y. So therefore, S equals 2 square roots of 4 minus y. All right, so I can use that to find all of the areas of these shapes. So for part A, if my cross sections are squares, the formula for the area of a square is a side squared, or S squared, so I would be integrating 2 times the square root of 4 minus y, that quantity squared. My variable of integration is dy, so make sure you put in your dy. And the limits of integration now for this problem, since everything's in terms of y, I have to go from my smallest y value to the biggest y value. So that would be from 0 to 4. And if you type that into your calculator, you get 32. All right, B, equilateral triangles. The formula for equilateral triangles is square root of 3 over 4 s squared. So the square root of 3 over 4, and then the integral of s squared. So 2 square root of 4 minus y, the quantity squared, dy, from 0 to 4. And that ends up being 8 square root of 3. For rectangles of height 4, the length of the rectangle is still S, and then the height is 4, so the area of a rectangle is length times height, so 4 times S. It doesn't matter whether you put the 4 inside the integral or outside of the integral, since it's a coefficient. So I'm going to do 4 times the integral of 2 square root of 4 minus y dy from 0 to 4. And that answer ends up being 128 over 3. For your isosceles triangles with one leg in the base, the formula for an isosceles formula for the area of an isosceles triangle is 1/2 side squared. So 1/2 integral of s squared dy from 0 to 4 ends up being 16. For your semicircles, the area of semicircle is pi over 8 s squared. So we have pi over 8 integral of s squared. From 0 to 4. And that ends up being 4 pi. F are rectangles of height 5y. This is kind of similar to the last one on example 2. The length of the rectangle is still s, or 2 square root of 4 minus y, and the height is 5y, so the area of each rectangle is 5y times s. So I have to integrate 5y times s is 2 square root of 4 minus y dy from 0 to 4. And if you look back on part C of this, I could pull the height of 4 out in front of that integral since it was a coefficient, but 5y is a variable, so it has to stay inside the integral. You could pull the 5 out if you wanted to, but the y has got to stay inside that integral. All right, and that ends up being 256 over 3. All right, let's look at this last example. The region in example 3 models the surface of a lake. At all points in the region at a distance x from the y-axis, the depth of the water is given by d of x equals 1 minus x squared. Find the volume of the water in the lake. All right, let me just redraw this parabola that we were dealing with right here. So there's the surface of the lake, is that same region that we were dealing with in part 3. Now, the part that it says at all points in the region at a distance x from the y-axis, the depth of the water is given by dx equals 1 plus x squared. That means that if I pick any x value, say right here, then all the points that are x distance from the y-axis, which would mean all of those points on that vertical line, at all of those points on the surface of the lake, the depth of the water is 1 minus whatever this x value is squared. And then whatever this x value is right here, then all the points that are at a distance of that x value from the y-axis, meaning every point on this vertical line, then whatever that x value is, the depth at all of those points on that vertical line is 1 minus that x value squared. So essentially what they're telling you is that the cross sections of this lake have a specific shape, and that specific shape is a rectangle, because this would represent the length of the rectangle, and because this rectangle is a vertical rectangle, then I'm back to having everything in terms of x. So this is the length of my rectangle, so I can call this the S that I've been calling all of these cross sections. So here S is now vertical, so then I have to do top minus bottom. So in this particular problem, S is going to equal 4 minus x squared, because the equation of the curve is 4 minus x squared. That's the top of the rectangle minus the bottom of the rectangle is 0. So the length of the rectangle is 4 minus x squared. Now, if you picture, we're looking at a bird's eye view of this lake. So the depth of the lake along every single point in this vertical line is 1 minus x squared. So the cross sections are going downward instead of being built upward, which is the way we visualized some of the other ones. So these cross sections going down to the bottom of the lake have a length of 4 minus x squared and then a depth of 1 minus x squared. So the area of each cross section is 4 minus x squared times 1 minus x squared. So then, just like all the other cross sections, if you have a whole bunch of cross sections, then what you want to do is you want to integrate the area of that cross section to give you the volume of the entire figure. So that volume would be the integral of length times width, or S times D, 4 minus x squared times 1 minus x squared. And our limits of integration, since everything's back in terms of x, our limits of integration are going to go from -2 to +2. And if you type that into your calculator, you actually get exactly 19.2. Okay, this is a little different than what I usually expect you to do, but the next part of this does have some homework on it, and I do expect you to finish these homework problems before you get to class tomorrow. But I want you to practice the rest of these notes for today, the part that says homework. It's basically 2 problems, 2 graphs that you have to sketch, but then I ask you to find the volume for several situations. You need to work all of those problems before you get to class tomorrow, please.